So I looked up the mass of a tennis ball, and it turns out a tennis ball is about 58 grams or 0.058 kilograms. And I wondered if we shot that tennis ball to the right, straight toward a golf ball, and I looked up the mass of a golf ball is about 45 grams or 0.045 kilograms. So if we shot these balls straight toward each other at a certain speed, let's say the golf ball is moving around 50 meters per second, that's pretty fast. It's over 100 miles an hour. And we shoot the tennis ball to the right at a speed of 40 meters per second so that these balls collide, and they collide head on. In other words, I want them to collide and stay in this single direction. I don't want a glancing collision where the golf ball like goes flying up this way or something like that. Let's not do that. So it's all going to happen in one dimension. And my question is this: just given the initial velocities and the masses, can we figure out the final velocities of the golf ball and the tennis ball? Let's try it. So how can we start? When I'm doing a collision problem, I typically just start with conservation of momentum. I just know if it's going to be a quick collision, the momentum right before the collision should equal the momentum right after the collision, at least the total amounts. Why is that true? It's because this golf ball, the time that it's actually in contact with the tennis ball, it's going to be so small that any external forces that might be there, like gravity, are going to have so little time to act on this system. The external forces can't really impart a large amount of external impulse. And if there's no external impulse, the total momentum of our system, golf ball and tennis ball, has to stay constant. So because these collisions happen typically over a very short time interval, we're just going to say the momentum right before total and the momentum right after total is going to be the same. And that goes for basically any collision between two freely moving objects. You can just assume the total momentum is going to be conserved. So what would that mean mathematically? Well, it's going to be that the total initial momentum, P is the letter we use for momentum, and the total, I'm going to use sigma to represent the total. This just means add up all the initial momentum, not just the momentum of one of the objects, but all the momentum of all the objects. And I'm even going to put a vector sign up here because momentum is a vector. That's important because momentum can be negative, so you can't forget the negative signs in here. And if momentum's conserved, then this initial total momentum should equal the final total momentum. This is what we mean when we say momentum is conserved. So remember, the formula for momentum is mass times velocity, so the initial momentum of the tennis ball would be mass times velocity, so that'd be 0.058 kilograms times the velocity initially of the tennis ball is positive 40, and I'm going to put a positive here to remind me that this is to the right. That's why I'm making it positive. The initial momentum of the golf ball would be also mass times velocity, so it'd be plus. The mass of the golf ball is 0.045 kilograms, and the initial velocity of the golf ball would be negative 50 meters per second. Because the golf ball is moving to the left, and we're going to assume leftward is negative and rightward is positive. So if this is the total initial momentum and momentum's conserved, this should equal the total final momentum. So the final momentum of the tennis ball is going to be 0.058 kilograms times V final of the tennis ball. I'm just going to call that VT for V of the tennis ball. Plus the final momentum of the golf ball is going to be plus 0.045 kilograms times the final velocity of the golf ball is going to be V. I'm going to put VG for V of the golf ball, and this is going to be the velocity after the collision. So can I solve now for the final velocity of the tennis ball and the golf ball? No, I can't. I've got one equation and I've got two unknowns sitting over here. So I'm not going to be able to solve for either of them if I've got two variables in my single equation. In other words, I can add up this whole left-hand side if I wanted to. If you add all this up, you're going to get 0.07 kilogram meters per second is your total initial momentum. And if I solve this over here, I'm going to have equals two unknowns. I don't know VT, and I don't know the velocity of the golf ball either. So I need at least one more piece of information. I need to know, for instance, if I knew one of these final velocities, I could easily solve for the other. So if the problem gave me the final velocity of the tennis ball, well, I can plug that number into here and just solve then for my final velocity of the golf ball. Or the problem could tell you that this collision, what type of collision is it? If it tells us that they stick together, then I can assume that they both move off with the same velocity. That would be a perfectly inelastic collision. So if it was a perfectly inelastic collision, I'd just have equals one big mass over here. In other words, 0.058 kilograms plus the mass of the golf ball 0.045 kilograms. It'd be one big mass because they stick together in a perfectly inelastic collision times just one final velocity because they're both moving at the same velocity. So I could take this 0.07, divide by my total mass, and that would give me the final velocity of the two balls combined. But that's unlikely. These balls aren't going to stick together. I mean, a golf ball and a tennis ball, unless you've got some sort of adhesive on the front of them, I don't think these are going to stick together. That seems unlikely. So let's assume that doesn't happen. But if you were told they stick together in a collision, two masses, that's what you could do. It's much more likely that if you're dealing with a golf ball and a tennis ball, that you're going to be told that this collision was elastic. And remember, elastic means that the total kinetic energy in this collision is going to be constant or conserved. You're not going to lose any of that kinetic energy to any thermal energy or sound. And it turns out just being told this, that the collision is elastic, is enough to solve for these final velocities. And the reason is this is implying that kinetic energy is conserved. So we can use that to our advantage. We can just say, all right, not only is momentum conserved now, but if we say it's elastic, that means the total amount of kinetic energy is conserved. So the initial total kinetic energy has to equal the final total kinetic energy. And remember, kinetic energy is 1/2 mv squared. So I can say that, all right, 1/2 0.058 kilograms, the mass of the tennis ball, times its initial velocity was 40 meters per second. You can't forget to square it. Kinetic energy is 1/2 mv squared. And then I do plus the initial kinetic energy of the golf ball is going to be 1/2. Mass of the golf ball was 0.045 kilograms. We multiply by its initial speed squared, and I'm just going to do positive 50 because we're going to square this. This is just the speed in kinetic energy. It doesn't matter whether you make it positive or negative. Over here, it definitely matters in momentum whether you make it positive or negative. But since you're squaring it, and since kinetic energy is a scalar, it can't be negative. Doesn't matter whether you put the positive or negative in here, it's going to go away when you square it. We can say that this total initial kinetic energy should equal the total final kinetic energy. So I can say that this total amount here should equal, I'm just going to put the equal sign down here, the final kinetic energy of the tennis ball would be 1/2 0.058 kilograms times the final velocity of the tennis ball squared. And then I have to add to that the final kinetic energy of the golf ball, which is going to be 1/2. Mass of the golf ball was 0.045 kilograms times the final velocity of the golf ball squared. And you might be like, how does this help us? Look at how horrible this looks. These are squared. How's this going to help me now? Well, now you can solve because I've got two equations and I've got two unknowns, and the two unknowns over here are the same as the two unknowns over here. So whenever you have two equations and two unknowns, you can solve for one of your unknowns. You can actually solve for both of your unknowns. We're just going to solve one of the equations and then substitute into the other, and we'll get one equation with one unknown. In other words, let me show you how that works. Let me clean up this side over here, this left-hand side, which is kind of like the upper side right here. So if I add up all this initial kinetic energy over here, I get 102.65 joules of initial total kinetic energy. But I've still got two unknowns in this equation, so what I'm going to do is I'm going to come over to here. Let's just solve this for VG. If I solve this for VG, I'll subtract 0.058 VT from both sides, 0.045 VG. And now I can divide both sides by 0.045. Over here, 0.07 divided by 0.045 is equal to 1.56. And 0.058 divided by 0.045 is equal to 1.29. And then this is multiplied by VT. That's what's equal to VG. So I have an expression for VG, the final velocity of the golf ball, is equal to this quantity right here, 1.56 minus 1.29 VT. So I'm going to take this whole expression, which is equal to VG, and I'm going to plug it in right over to here, which gives me 1/2 0.045 kilograms times the quantity 1.56 minus 1.29 VT squared, because this VG was squared, and I'm just substituting the expression I have over here for VG in for this quantity VG, and I still have to multiply by the 1/2 and the 0.045, and I still have all of this, so I still have 102.65 joules equals 1/2 0.058 kilograms times VT squared plus this quantity right here, which is what I substituted in the VG for. And it's getting a little messy, but at least I now have one equation with just one unknown. I just have VT in here. So if I do the math, I'm gonna have 102.65 joules equals, if I just take 0.058 divided by 2, I'm gonna get 0.029 and VT squared. I'm gonna leave off the units, things are gonna get messy. And then if I take 0.045 divided by 2, I'll get 0.0225. And now I've got to square this quantity. So if you remember, if you ever have a minus b squared, the result of that is going to be a squared, which is 1.56 squared, minus 2 times the quantity of the first one, 1.56, times the quantity of the second one, which is 1.29 VT, and then plus the final element here squared, this b squared, which is going to be 1.29 squared times the velocity of the tennis ball squared. That may have made no sense at all. If so, what I'm really doing is I'm saying that if you ever have a minus b squared, that's just equal to a squared minus 2ab plus b squared. And that's what I did. Here's my a. I did a squared, 1.56 squared. And I did minus 2 times this first one times this second one with the VT in there. And then plus b squared is going to be plus this final term squared is 1.29 squared times VT squared. So I've got this big mess now. I just need to clean it up. The left-hand side is still 102.65. I've still got this 0.029 VT squared sitting here, but I need to multiply this 0.0225 throughout this whole quantity because it's multiplying this whole quantity. So if I do that, I'll get plus 0.0548. That's what 0.0225 times 1.56 squared is. Then I'll get minus 0.0906 VT. That's what 0.0225 times this whole quantity is. And then finally I'll get plus 0.0374 VT squared. That's what 0.0225 is times this quantity right here. So let's identify the VTs. I've got a VT right here, just single VT, and then I've got a VT squared right here. So I can combine this VT squared term with this VT squared term, and I'll get 0.066 VT squared minus 0.0906 VT plus 0.0548. Now we're getting close, I promise. If we subtract this 102.65 from both sides, we'll have 0 equals this whole quantity again, and then 0.0548 minus 102.65 is going to be negative 102.595. And what this is right here is a quadratic equation. And you can't solve this by just trying to isolate VT on one side. It's never going to work that way. You've got to use the quadratic formula. So in the quadratic formula, this term here, the 0.066 would be A, and this negative 0.0906 would be B, and this negative 102.595 would be the C. You could either do this the long way by hand, or you could just use a quadratic formula solver. They're available online. They might be on your calculator. That's what I'm going to do. I'm going to do this in my calculator. So the two answers I'm getting out of this would be VT either equals, I'm getting 40 as one answer, meters per second, or I'm getting negative 39 meters per second. And so which one is it? Is it going to be 40 or negative 39? Well, we can figure out which one it is. Look at this VT here, 40. That's the initial velocity it had already. We want the final velocity. Why is it giving us the initial velocity again? Because it turns out one way to conserve momentum and energy is for these objects to just miss each other and fly right past each other. If the golf ball doesn't actually collide with the tennis ball and the tennis ball just keeps going forward, they just both maintain whatever velocity they had initially, and that would correspond to this. This is a collision that missed. So we know that this collision was not the one we're looking for. That's if they didn't collide. We're looking for this velocity right here. So after the collision, this tennis ball gets knocked backward with negative 39 meters per second of velocity. So how do we find the velocity of the golf ball after the collision? Well, I've got the velocity of the tennis ball. Now all I have to do is bring that right back into here, and I can get what the velocity of the golf ball was. The velocity of the golf ball is now just going to be 1.56 minus 1.29 times this quantity, negative 39. And if I multiply this out, I'm getting about 52 meters per second, positive 52 meters per second for the velocity of the golf ball. That means this golf ball got knocked back to the right because it's a positive velocity, and it got knocked out at a speed of 52 meters per second. So recapping what we did, we were given the initial velocities and the masses. We tried to use conservation of momentum, and that was fine, except we had two unknowns. So we had to write down another equation. If we're told this collision is elastic, we know that total kinetic energy is conserved. We wrote down that equation, but it also has two unknowns. So we solved the momentum equation for one of the variables, Vg. We substituted that expression into over here for the Vg in this kinetic energy. We squared it. We had only one equation with one unknown, but unfortunately it gave us a quadratic equation. So we used the quadratic formula to solve. One of the velocities corresponded to the same as the initial velocity the object had in the first place. We don't want that one because that would mean they didn't collide at all. We take the second one. If we want to find the velocity of the first object, then we take that, we plug that back in to this expression here. We get the velocity of the other object.